Imagine you were asked to predict or forecast how these two lines would behave in the future. If you trained a predictive algorithm on these data points, you would discover that the initial straight line trend is actually the beginning of two exponentially decreasing curves. Predictive algorithms are powerful in making forecasts where you have too little data to understand the behavior of a system using your own intuition. Unfortunately, many data sets available today are flawed by inconsistencies and may look more like this. If you used the same predictive algorithm to forecast how these data points will behave in the future, you will find that it produces a wildly inaccurate forecast. It is in situations like this where a methodology should be used to bring some form of consistency to the inconsistent dataset. This will allow the predictive algorithm to more accurately and reliably forecast the system's future behavior.
This is exactly what we have created, a methodology that harmonizes datasets so they can be used for accurate predictions. The methodology begins by creating an area of truth bounded by margins of acceptability, which enclose the original data point. These margins of acceptability encompass a subset in which a potential consistent dataset could lie. To find this subset, the methodology iteratively manipulates the distribution of the dataset within the so-called area of truth, causing the individual data points to rapidly translate between their vertical limits. With each generation of a potentially consistent dataset on the left, a fresh forecast is also created on the right. By analyzing the rate of stray of the new forecasts from the trend of the original dataset, we are able to select progressively more accurate forecasts and more consistent datasets. This iterative loop will eventually converge on a highly consistent dataset, which will allow for an accurate system dynamics model to be generated. As can be seen in the graph on the right, this model forecasts behavior which very closely mimics the original exponentially decreasing curves that were predicted, using completely consistent data at the beginning.
If we compare the original inconsistent dataset to the newly created consistent dataset, we can see how the methodology has transformed the data points. As a final example, we have also applied the methodology to the Lorentz system, which has three states and is chaotic. Because of this, forecasts, even when they have been generated from perfectly consistent data, are expected to mostly but not completely follow the trend of the Lorentz system's future behavior. It is no surprise then that an initial prediction made on a very inconsistent dataset is immediately inaccurate. However, yet again, when we apply the consistency methodology to the data and iterate through thousands of candidate datasets, a consistent dataset is eventually selected. The predictive algorithm, trained on this, models and forecasts the behavior and trend of the evolving system extremely well. This result impressively demonstrates the consistency methodology's ability to enable accurate forecasting with very little and very inconsistent data.